let's talk about this guy, Albert Einstein. Smart dude, right? Um, so one of the things about Albert Einstein you may not have heard of is this idea of what it was called, what a lot of physics people call the miracle year. The miracle year is when Albert, we're on a first name basis, by the way. When Albert was working in a patent office in Switzerland, and basically while he was working a full-time job, right? This is nothing we can do these days, right? He published 4 different papers, right? Which all of them, to me, deserves like a Nobel Prize for, but he got the Nobel Prize for one of them only. Does anyone know which one? Actually, which one?
Or no, the mass energy equivalent.
Right. The mass energy equivalent. That's not correct, but that's what you think, right? E equals mc squared, right? That's like a super famous equation that everyone knows, right? Even non-science students, right? Okay. So mass energy equivalence basically tells us that, well, energy can be converted into mass, right? So if you're or in the sun, right, where fusion is happening, the sun is basically converting mass into energy and giving it off as light. That's how we are alive around here, right? Okay. And this is how all of fusion and fission occurs. Basically, all of the energy of the universe is from these processes, right? And that's just you would think that you should win a Nobel Prize to figuring that out, right? When no one else realized that at first. Okay, let's go backward up to here. Special relativity. So how many of you guys are in modern physics right now? Okay, about 2 or 3. Okay, so in modern physics, I think the first thing they'll cover is relativity, where when you have objects moving, relative at the speed of light, right? Different things starts happening. Stuff that are non-intuitive starts happening. Okay, you have these effects called time dilation, right? Length contraction, right? Contraction, right? Basically, time slows down when you start moving closer to the speed of light, or things starts looking shorter, right? So you have a meter stick here, right? Right? I look at this meter stick. I say this is 1 meter, right? I define this to be 1 meter, right? You have a spaceship. Let's say you're in a spaceship flying by really fast, right? From your observation, it will physically look like half the length, right? And that's known as length contraction. Things look shorter when you're going fast, okay? And this is what I think he should have won the Nobel Prize for when I was your age, okay? Because this is like super cool because it's a way of thinking about space and time that no one has thought of before, okay? Right? Brownian motion. Anyone remember what that's about? I'm gonna draw a bunch of little dots. Let's say you have a little flask of, water, and then you have flower pollen in them. You don't have to draw this. This is just me silly squiggling stuff, right? Right. What happens when you have little particles or flower pollen in a little liquid? Do they just stay still? What happens to them?
Random.
Right. They move randomly, right? So so each of these will have its own little velocity trajectory. They run into each other, so they change direction also, right? So this basically gives you like all of chemistry, right? All of chemistry comes from that. Okay, not just that, but also like a lot of our devices, um, such as a semiconductor that's inside our computer, basically utilizes this concept of having random motion at the atomic level in order for things to kind of stay in motion. Okay, so that means when temperature is not equal to 0 Kelvin, everything is moving around. Okay, and that is a concept that how many of you guys have thermal? Maybe the seniors. So yeah, maybe I'll take it next year. Okay. The last one is the photoelectric effect, and this is when I was your age, I thought, yeah, this is such a simple thing. I could have figured that out, right? But probably not, right? Where you have light. let's say you have some sort of light, and in physics we tend to draw lights as a little squiggly line because it is a what? What is light? What type of, is it a wave? And also what? An electromagnetic wave and a particle at the same time, right? So this is the particle wave duality, right? Duality. And this not only happened with light, with everything, right? The atoms inside me also exhibit particle wave duality, but just at a much shorter wavelength. And what happened here is that, right, you have light, which is usually with the sign gamma. It's like okay? And what happens when the light hits it, it ejects a little electrons off of it, okay? And this is stuff that you'll see in modern physics, those of you who are taking it this semester, okay? And this was kind of simple things like that. I mean, I could have figured that out, right, when I was your age, right? Oh, you have some energy that goes into your material. That energy has to go somewhere, right? Right? The lightest thing in an atomic structure is the electron, right? So you think, oh yeah, oh, whatever flicks off will be most likely an electron, right? If you get in high enough energy gamma ray, you can actually start ejecting protons also, but that's at a much higher energy. Okay. And sorry, can you pronounce your name again? Sorry. Josue? Right? You thought it was the mass energy equivalent, right? Because this is the most famous thing, right? That would make sense, right? I thought of special relativity because it's like, oh, that's super cool. It's like, oh, time and space doesn't actually work the way we think it works, right? Okay. It turns out he won the Nobel Prize for the photoelectric effect. What I thought was the simplest thing. Okay. Okay. And why did he win the Nobel Prize for that is because that actually has, all four of these has a huge effect on everything we do every day, okay? But all of today's technology, your computer to your cameras, right? Everything we do today is based on this, okay? And I'll show you why, okay? So, right, a camera such as, all of you guys probably have one on your phone right now, right? The little camera is a digital sensor, right? What happens is that when light hits your little digital sensor, right, it converts that light into a little electrons that gets captured by some electronics. Uh, let's just draw boxes right now. Let's not draw these symbols, right? Some sort of electronics so that you can do a computation on it, right? Either store it, do computation, whatever you want. Computation, right? Because that's what your camera is doing, right? So when you unlock your phone and you turn on your camera, right? Light hits your camera, it converts that light into some sort of electrical signal, right? In order to store it in your phone, right? And then that's why you have Instagram and whatever the hell you guys do these days, right? TikTok, right? Do people still use TikTok or is that outlawed now? Okay. Okay. So any time you have a camera, any image that you capture, right, is based on the photoelectric effect, right? It allows you to convert light into electrical signal, right? Right? And why do I say like, like that's the most encompassing technology these days, right? All of like, all of what Google does that, records all of our information, all the facial recognition it does and stuff like that, is based on camera capturing information, right? Right? Every camera everywhere, Google has access to that data, right? Every time you walk down the street, right? So all of these large data set, right, is from the photoelectric effect, and therefore all these large data set produces, machine learning, self-driving car, ChatGPT, all of this stuff, right, is created because someone in 1905 realized you can convert light into electronics, convert light into electrons. And these electrons eventually becomes electronic signal that we're going to learn how we can actually manipulate that, okay? And that's what this whole class is about. Being able to manipulate electrons so that you can, make computers, phones, and, take over the world, whatever, whatever evil villains do, right? Okay. right? So this may not be as clear because in these little digital cameras, right? There's like, I don't know, like 12 million of these little pixels, right? And the wiring are integrated into your phone, so unless you want to ruin your, even if you take your phone apart and you look inside, you won't be able to see the wire because they're so small, right? You need a microscope to even see the wires. Okay, so I'm going to show you guys a picture of a simpler version of it. This is actually an experiment that, that I'm currently working on. So inside here, if I can draw on top of this thing, it's basically just think about it as like a little light sensor. When light comes in and hits this little sensor, it produces a little bit of it uses the photoelectric effect, right? It creates an electron, and those electrons flows down a wire. Okay, I'm trying to remember where does this go? Okay, okay, okay. Oh yeah, so it flows down some wire up to here into what's known as an amplifier. Who knows what an amplifier does? Who has heard of that before? What's an amplifier? Speakers, right? So when you have a low volume something coming in, an amplifier makes it louder, right? It amplifies the signal, right? Okay, and this amplified signal, right, it gets passed into both of these things. Let's just talk about the digitizer. Okay, so now you have some sort of signal, some amount of electron, a bunch of electrons, right? And supposed to one electrons, you have billions and billions of electrons, right, flowing into here. This is known as a digitizer. I should change the color so you can actually see it. Okay, it's known as a digitizer. Okay, and what this does is that it converts, whatever waveform, whatever shape of signal in here into a digital number. So and converts all these stuff into, let's just do this on the bottom here, right? Okay, ones and zero, 0, 1, 1, 0, 1, 1. So those of you who are computer science major might be familiar with binary numbers already, but if not, then we'll get to that part, okay? Right? So now you have all these ones and zeros. Now you can store them into a computer and then send it to your phone, send it to your friend, right? Basically, all these ones and zero, either becomes, some sort of like signals, or a picture of someone walking a dog, because that's the most interesting in our life these days, right? Whatever that is, whatever you guys do with Instagram or TikTok, right? Okay. So what we need to talk about is that, let me highlight this box right here. All of the stuff up to the point of the digitizer, all this red stuff, is known as analog electronics. Analog electronics. Okay? It's stuff that's not digital. Okay? Just think about it as, if it's not digital, then it's probably analog, right? And that's what the first half of the class is going to be about. Okay? How do you store analog signal? How do you amplify it? How do you transmit it? Right? How do you hold it for a little while? Okay? And that's what the first half of the class is going to be about. The second half of the class is going to be about digital electronics. Okay? So that's why in Santa Barbara, when I took this class, is actually two classes, where one class is on analog electronics, the second half is on digital electronics. But we're going to do them all at the same time, okay? Because we're only allowed to have one electronics class here. Okay. So, any questions or comments about what this whole class is? Basically, that's what this whole class is going to be about. How do you deal with analog signals? Basically, just little electrons running around, right? And then we're going to figure out how to digitize that, and then using the digital signal, we can actually do fancier stuff. Okay. Any questions? Should have brought a drink of water. What time is it? Do you guys want to take a 10-minute break? Come back at 2:50, and now I'll do like 30 minutes of actual lecture about the start, and that way we can get through the material for this week. Okay? Yeah, let's take a 10-minute break. Okay, I'm gonna pause. Is there a pause button?